Okay, so this week I wanted to talk about the electric field of a continuous charge distribution. But before we get into the details, let's recall for a single point charge Q, the electric field is given by this expression here. Where is my pen? There's my pen. K, right, this constant, times the amount of charge Q has, divided by how far away you are from Q squared. So, for example, right, here's a positive charge. I want to know what the electric field is. Some distance r away. Here's r. And r hat, this is actually just a little vector. It's called a unit vector. You maybe remember those from your math class. Here's r hat. It points in the direction of the radius and has no magnitude, so you can multiply it by anything and it won't change the magnitude, it only gives direction. It's just a kind of a bookkeeping device for direction for vectors. So let's get rid of that, make this bigger. Now if we have several point charges, well, because the electric field obeys the principle of superposition, I can simply add up the electric fields from all of them. This is essentially saying that the electric field total is equal to the electric field due to one point charge plus the electric field due to a second point charge, and so on, where this is a vector sum. So I can have a positive charge here, a negative charge there, a couple more positives, twice as charge here, and I want to know what the electric field is right there. Well, here's 1, 2, and 3. The electric field due to the first charge might look like this. Here's E1. E2 is going to point toward 2, but maybe is a little bit stronger because we're closer. So here's E2. And then E3, well, we're further away, but there's more charge there, so it'll look something like this. E3, and so on. So you'd add all of these up like vectors. It's pretty ugly looking if it's not very symmetric. But now let's say we have lots and lots of charge. Well, we're going to take the calculus limit, where instead of this delta Q, right, each of these is a delta Q, I'm going to make them smaller and smaller and call that a dQ. For example, let's say I have a rod that I charged with fur, like a plastic rod, rubber rod, and there's a continuous charge distribution on it. It's uniform, right? So it's spread out evenly throughout it. What this dQ means is basically I take a little piece of this rod, and the amount of charge on that little piece we call dQ. Now, to figure out what dQ is, I'm going to make a couple of definitions, and I'm going to go in backward order since I chose to start with the rod. Let's say the rod has a total length L and a total charge on it Q, big Q, okay? Then I'm going to define the linear charge density lambda as the total charge divided by the length of this thing. That's it. That's the linear charge density, which means I can rewrite this as lambda is equal to dQ over a little piece, dl, right? So I can make this little itty bitty distance, that's a dl, or if I define my my coordinate axes, that might turn into a dx or a dy, depending on what direction everything is. And then I take this and I solve for dq. So dq is equal to lambda dl. There we go. Now I might have a surface charge density. So for example, one of the plates of a parallel plate capacitor, again, has charge uniformly spread out across its surface. But remember, it's very thin, so I don't care about, how thick it is, right? That's all very thin. It again has a total charge Q and an area equal to A. Then I can define the surface charge density as the total charge divided by the total area, or I can say that sigma is equal to a little bit of charge over a little piece of the area dA, where a little piece of the area might be this little piece right here. It might be a dx times a dy, for example. So then I have dq, if I want to solve for dq, that's simply equal to sigma dA. Lastly, I might have a sphere, for example, like we had in lab. Oops, sorry, I did blue. Let's pick a different color. How about lavender? I might have a sphere of total charge Q and volume V. volume V. And again, the charge is uniformly distributed throughout all of it. The volume charge density, rho, Greek letter rho, is defined as the total charge divided by the total volume. Once again, I can, because it's proportional, right? The reason this all works is these are proportional to each other. The total charge divided by the total volume is equal to a little itty bitty bit of charge, dq, divided by a little itty bit of volume. And I've never been able to draw a little itty bitty sphere inside of another one, but you can imagine it's kind of like that. Okay, and then I'm going to, we'll see what we're going to do with an example. So we have three ways of writing what this dq is depending on the situation we have. Do we have, are we dealing with a volume, a surface, or a line of charge? All right, let's do this example. A ring of radius A carries a uniformly distributed positive total charge Q. Calculate the electric field due to the ring at a point P lying a distance x from its center along the central axis perpendicular to the plane of the ring. So as always, the first thing I need to do is draw a picture to make sure I understand what I'm doing. Maybe I can draw an ellipse. I don't know if it looks like that. Oh, how about we do this one? Transparent. All right, here we go. Well, that's not an ellipse, that's a circle. There we go. So here is a ring of charge. So it's got, right, positive charge all the way across, all the way around. This is sort of a, perspective. It really is circular. And I want to know it's got a radius A, that's important. It carries a uniformly positive total charge Q, and I want to know what the electric field is at a point P lying a distance x from its center along the axis perpendicular to the plane of the ring. So this is the axis they're talking about. Right, here's our x-axis. This is where the center of the ring would be. And I want to know what the electric field is here at this point. What is the electric field here? Okay, well, what's important to do is now we're going to need to draw, I'm going to rotate this again, so I'm really looking edge on to this ring. So here it is, edge on, and then maybe we'll get that's a thick line, isn't it? And there's our x-axis. And so we have positive charge around on this ring. This is like the side view, and I want to know what the electric field is at this point. Well, I'm going to take 2 points. I'm going to take this little itty bitty point at the very top and this little itty bitty point here at the bottom, and I'm going to see what the electric fields are due to those 2 points. Okay, and just consider those for a moment. So the electric field due to this little charge dq1, right? If this is a positive charge, right? Because the whole thing is positively charged. The electric field points in a line pointing away from dq. So I'm going to call this dE due to this little itty bitty charge there, dq1. Likewise, the little itty bitty bit of charge that's at this point too, I'm going to call dq2, and it creates an electric field radially away from this, like so, dE2. Oops, and these are vectors. Now notice that these vectors are somewhat symmetric. So what would happen if I add dE1 plus dE2? Well, the vertical components are going to cancel with each other. They are equal and opposite, and all I have left is a component in the horizontal direction, doesn't like it when I go back and forth, plus the second one happens to be right about there. So this vector is the sum dE1 plus dE2. There. Okay. So that's convenient. What that means is I can ignore the vertical components of the electric field for all of these points, and I only have to add up the portion of the electric field that points in the x direction. So dE1 plus dE2 is equal to dE1, comma, in the x direction plus dE2, comma, in the x direction. So that's really convenient for me because I can simplify things this way. Okay, so let's make it a little more complicated. So let's figure out what one of the magnitude then of this little dE would look like, okay? So in general, our electric field due to some charge, I don't know, I, let's call it, is going to be, as we saw before, K dQi divided by how far away we are. Well, how far away are we? Let's do 0.1. So this distance R1, I can put, or R sub I if I want to be generic, Ri squared. If this, so this would be the magnitude of the electric field due to one little piece of charge right here. Now, if I only want the x component of this, dEi, comma, sub x, well, I need an angle. Let me draw my angle. I'm going to define this angle as theta. Oops, theta. Then that means that this angle, right, is also theta. Here's my dE1. I want only the portion that's in the x direction, so I want the cosine. So I've got K dQi over Ri squared times cosine of theta. Okay, so far so good. Now, let's figure out what R is. So R is the hypotenuse of a triangle, where this is the distance x, right? From the question, I want to know what the field is at a distance x. So x can show up in my answer. I've given the answer here so I know where I'm going. And this, what distance is that? Well, that's just the radius of my circle, right? And the radius of the circle is A. So here's A. So R is related to A and X by Pythagorean theorem. So R squared is equal to A squared plus X squared. So I can plug that in down here. And notice that this distance is the same for all of these charges. This point P is equidistant to all of these charges. So that's actually going to be really nice. It's going to come out of the integral once I get to that point. So K dQi divided by now A squared plus X squared times cosine of theta. And, well, I don't know what theta is, but I can define theta based on these values A and X. So cosine of theta, because that's what I have here, cosine is opposite over hypotenuse, is A over R. No, cosine is adjacent, excuse me. That's why I need you guys in front of me to catch my mistakes. Cosine X over R. Again, R, though, is this thing, well, square root of that thing, so I can write this as X over the square root of A squared plus X squared. Okay, so I can put that in for cosine. K dQ sub I over A squared plus X squared times X over A squared plus X squared to the 1/2 power. Now, if I have some number square rooted times that number again, well, I can simplify that again. This becomes kx dq sub I over A squared plus X squared to the 3/2.